Okay, great. So yeah, here's some pictures from
Start.
Imperial days. That's my lacrosse team on the top right. Top left, I did a lot of kung fu when I was at Imperial. They have an amazing wushu kung fu team. Many of you may be familiar with it. It had a great University of London, it was at the time. Sports teams, a lot of that. And I was studying physics in the physics department, and also spending my summers as an intern at NASA and beginning to think about maybe being a space scientist. So I had 4 wonderful years with you all, and then set off for Leicester to do a PhD in space physics, focusing on the Earth and its environment, which I'm going to talk a lot about as we get to the science part. So had opportunities to go to Svalbard, which is that top right-hand picture there, and run these massive radar dishes, the ISCAT radars. And top on the left-hand side, we are on Iceland. We built this radar system you can see here. So lots of opportunities to kind of do field work and do physics. And that was what I really loved, is just the chance to leave my desk once in a while, as you'll see as I give this talk. And I took up high altitude mountaineering while I was at Leicester. Actually, as soon as I left Imperial, that summer I went off and started climbing mountains and set off for Argentina to start with. Decided I would try and climb the highest mountain in South America, which is called Aconcagua, 6,968 meters above sea level. I hadn't really climbed any mountains before, so it was a bit of a shock to the system, but I got completely addicted to mountaineering. And the top pictures there are Denali in Alaska, highest mountain in North America. And from there, this sort of mountaineering journey continued. So kept on kind of doing activities and being outside and loving climbing. But I moved to the US when I finished my PhD, had to get a real job, and was a research scientist, working again on the Earth's aurora and environment, and beginning to shift my direction slightly, because while I was working at NASA, their spacecraft Messenger got to the planet Mercury. It got there in 2011. And I was working there, and we got lots of the data back first. We're heavily involved in the instrumentation on this mission, on this first mission to Mercury, first mission to orbit the planet. So all of the data I'm going to show you today came from that particular mission, because that's the only data that we have of an orbiter around Mercury. But also I had a really great boss. He let me go to the Himalayas. So the left-hand picture is the Himalayas, a mountain called Ama Dablam. It's about 11 miles from Everest. 6,500 odd meters, technical ice and rock climb. And took up rowing while I was in the US, and to kind of keep fit, and joined this amazing kind of rowing squad. And we raced all over the world, became an elite lightweight rower, which was just a fantastic opportunity. So lucky to live near the water and have such an amazing team. And rowing was really interesting because, as I'm going to kind of mention later with the astronaut selection, lots of the skills that were required to think about becoming an astronaut one day, I managed to pick up through things like rowing, teamwork and leadership and communication skills and that kind of thing. And one of the real highlights of my career, which I'm just going to touch on but not really talk at length about, was that I got really interested in where all the mountains are in South America, because I was climbing more and more and more in the Andes, really enjoying the solitude, enjoying the fact that there's basically nobody there, and there's loads of regions that haven't really been explored. And so I decided to try to write some supercomputer code to identify all of the mountains in South America. And it sounds like it's easy to, like, where are the mountains? Just pick them out of the data. But actually, it's a slightly trickier problem than it sounds, because you might have a massive mountain, and on the side of that mountain, a boulder. At what point is that boulder, if it's really high up, at what point is it a separate mountain? And at what point is it just a lump on the side of a bigger mountain? This is kind of the kind of questions you need to, or the kind of code you need to write. So I started writing code on the supercomputer. I got some data taken by the space shuttle, actually, which measured the altitude of the Earth's surface. The data is on the right-hand side. There's about 85 million data points, I think, in that plot. So if you're going to analyze it all at once, you kind of need a supercomputer. And the color there is altitude, so you can see the kind of Andes Mountains running down the spine there in red of South America, and discovered a lot of mountains that hadn't been discovered before. The previous list was drawn up by this amazing Scotsman called John Bigger, with a map and a pencil. I have a copy of some of his notes and his map and kind of markings. But it's really hard to do a good job of identifying all the mountains, especially given how many there are, with a map and a pencil. So I made a list of mountains over 6,000 meters, and then mountains over 5,000 meters. I wanted to know the ones over 6,000 meters because my friend and I are trying to climb them all. Turns out that there are about 108, 110 mountains above 6,000 meters. I've done like 30 something. He's done 86, I think now, so he's towards the end. And then when we ran the code on mountains over 5,000 meters, we discovered loads of new mountains that hadn't been discovered before, that weren't on the previous lists. Many of them had no names and many of them had never been climbed. So spent the next few years just disappearing from the university as often as possible, and heading off into the mountains for a few months, trying to climb these unclimbed peaks, generally in a team of 2. Taking data at the same time. So sometimes there's data that scientists want to take that comes from really inaccessible regions. And so while we were up there, we'd often be taking samples or data for people. And that again sort of breeds a load of skills that are required, really, if you think about the kind of things you want if you want to be an astronaut one day. So things like resilience, things like, you know, thinking on your feet, thinking quickly, responding to things that go wrong, because things up there go wrong really quickly. And when they do go wrong, the consequences are pretty severe. The top right hand side, for example, that's antifreeze that Max is holding between his fingers. Antifreeze shouldn't be frozen at those temperatures. I can tell you why it's frozen later, but it broke the engine. So things go wrong, but also I learned a lot about teamwork and how to work with other people, and why things go wrong in teams, and you know, how to be a good team player, basically. So this was sort of all part of the journey, really. And I guess unintentionally, I ended up on a reality television series about astronaut selection. Didn't really mean to. It was kind of a strange set of circumstances. I was climbing in Argentina and I got an email from the BBC, and I came down just to get food and fuel for like a day. And I opened up my emails and there was one from the BBC saying, do you want to be an astronaut? And I just kind of applied, and anyway, I ended up on the show, and it was really interesting. Sort of like, I think of it as reality television. It's like the Bake Off meets space, basically. So they picked 12 people from their thousands of applicants, and they put us through astronaut selection to try and see who had the skills maybe to be an astronaut one day. So really interesting experience. And I now look forward to the next opportunity to apply for the European Space Agency astronaut program. But anyway, what I was asked to talk about today was space physics. And so the area that I work in is called magnetospheric physics, and I'm interested in studying how the sun interacts with the planets in the solar system. So this really lovely cartoon here, we have the sun on the left, and we have explosions from the solar surface, and these happen occasionally and fairly unpredictably and travel through the solar system, and they smash into the planets as they go. And what I would like to know is, what are the implications if one of these heads towards the Earth or one of the other planets? What could happen? Why do we care? And so the sun has a cycle of activity. This is kind of a representative shot of the solar surface in a given wavelength every year. It's an 11-year cycle. So you can see 96 was a really quiet sun, and then the sun, as you go around, this diagram kind of gets more and more active and then gets less and less active again. Actually, every 11 years, the sun's magnetic field flips. You know how the Earth flips on timescales of hundreds of thousands of years. The North Pole turns into the South Pole here on the Earth. Well, that happens on the sun roughly every 11 years. And the solar activity is linked to that flip in the magnetic field direction. And this has implications for us here on the Earth, the activity level of the sun. Well, we don't really notice it as we're sitting in the summer in our gardens. Actually, it does have implications if you're studying the magnetic environment of the Earth and how it interacts with the sun. And so this schematic just shows you some of the things that big solar events, big space weather events can cause. So for example, they can disrupt communications, they can cause damage to satellites, they can cause damage to human health if we have astronauts out there in space, disrupt things like GPS services. They can cause beautiful aurora, which is lovely. I'll talk about that more a bit later. Bright displays of the aurora that come really far south, which is nice. But there are downsides too. In fact, I put this up here actually just for my own entertainment. This is the National Risk Register. I think 2011, the government produces this every few years. And you can see sort of the relative likelihood of something happening in the next 5 years on the x-axis, and kind of a seriousness score on the y-axis from 1 to 5. I put it up here actually just because pandemic flu is well up there. You can see on the right-hand side, top right, probability 1 in 2 to 1 in 20 of happening in the next 5 years. Severity level 5 if it does. Well, we're all kind of suffering from some aspect of this. But what you can also see here is severe space weather. about the same probability. According to this government plot, as pandemic flu, slightly less serious at high 3, but you can see that actually it is a high 3, and when you compare with other things in that category, that's kind of an interesting thing. So things like flooding, volcanic eruptions, transport accidents, industrial accidents are on the same severity level. So I really want to talk today about Mercury, and in relation to space weather, one of the reasons why I'm interested in studying Mercury, and hopefully I'll be able to persuade you today that this is a good reason to think about Mercury, is that it sits in the inner solar system. It sits about a third to a half of the distance from the sun to the Earth. And so it sits much closer to the sun. It experiences much more severe space weather. And so if I really want to understand the physics of space weather at the Earth, a great place to start is looking at Mercury, because these huge space weather events at the Earth happen once every century or so. But at Mercury, they happen every day. So understanding the physics of the interaction between the sun and the planetary field at Mercury will help us to understand extreme events at the Earth. So I'm going to just show you this Mercury transit video, which I particularly like, just to give us a nice sense of scale to start off with. So this was actually taken in 2016 by a spacecraft that was that we'd launched, and you can see Mercury. I'm pointing on my screen, which doesn't help you, but you can see kind of this tiny dot passing through about a quarter of the way up the sun there from the bottom. So giving us a sense of scale of the sun and Mercury, and of course the picture in the background is changing wavelength, so you can see different features kind of popping out depending on the wavelength that we're looking at. But Mercury really kind of, you get the idea that it's sitting in the solar atmosphere, so close to the sun there, and such a tiny system as well. What else can I tell you about Mercury, just to get us started? A long day. Yes, it has a very long day. Its day is 59 Earth days. So it's spinning incredibly slowly. Its orbit is very elliptical. So rather than most of the other planets have more of a circular orbit, Mercury's is not circular. It's highly elliptical. It sits out of the ecliptic plane. That's what I'm trying to show you in the bottom here, with most of the planets sitting in the ecliptic plane, orbiting around, and Mercury kind of sits at, I think, inclined something like 7 degrees to the ecliptic. And it has really interesting something called 3-to-2 spin orbit coupling. And that means that I'm going to get this wrong now, 3 days on Mercury is the same as 2 years. So a Mercury day is 59 Earth days, and a Mercury year is 88 Earth days. So there are some really interesting things happening in Mercury's system. And we launched a spacecraft to Mercury in 2004. It took 7 years to get to Mercury, and it arrived in 2011. And this is Messenger, a NASA mission. We'd had a couple of flybys of Mercury before, a few opportunities just to glance at the system, but no orbiting spacecraft. And I'll talk a bit about why it's hard to orbit Mercury a bit later. But we got the spacecraft or NASA got the spacecraft to Mercury in 2011. And because it was the first one to orbit the planet, you kind of have to have a bit of a trade-off. There are lots of people that are competing for, and they have different requirements. And so people like me, I study Mercury's environment. I want to be some distance from Mercury looking at the environment. But there are people who are really interested in the surface processes and the geology and the history of the surface and its evolution. They want to be really close to Mercury so they can use cameras and look at high resolution images of the surface. And so you have competing teams there, and the inevitable resolution is a compromise, which is what we have here. So on the right hand side, this is not we don't need to study this in detail, but when Messenger orbited Mercury, it always got really close to the North Pole, and it never got close to the South Pole. So it looked at the northern surface in lots of detail and the southern environment, magnetosphere environment, but we never really saw the northern environment, and we didn't get close to the southern pole. And normally, under normal circumstances, that's fine, because actually these things are sort of mirror images of each other in terms of the broader magnetosphere. We could just take a mirror image. So the north is probably the mirror image of the south. Doesn't matter that we don't see the northern environment. I'm going to tell you in a moment why that backfired a little bit. But anyway, there were 6 questions associated with the Messenger mission. Why is Mercury so dense? What's the geologic history, the nature of the magnetic field, the structure of the core? Some of these are linked. The unusual materials at Mercury's poles, and what volatiles are important at Mercury. So let's just sort of start by thinking about the core, because some early results came from MESSENGER looking at that question. So here on this plot, what I've got for you is on the left-hand side, just a rough schematic of the Earth. So we can see we have a solid inner core, and then we have a liquid outer core, and we have the mantle and the crust. And you can see sort of rough proportions there. And on the right-hand side, you can see Mercury. And so one thing you should notice is that the basic structure is the same. We have a solid inner core and a liquid outer core, and we have a mantle and we have a crust. But the proportions are really different. So the core extends to about 85% of Mercury's radius. At the Earth, that number is about 50%. So take home, Mercury has is almost all comprised of the core, this iron with some impurities, and there isn't much mantle around it. So this is why Mercury is so dense. If you look at a plot of the planets, their density versus their other characteristics, what you find is that Mercury is just an outlier. It's really dense, much more dense than you'd expect it to be, and that's because it's nearly all made of metal. Okay, so why is that? Some lovely initial theories were brought up around how this could be. So this is not my over expertise, and I particularly like these pictures because these theories were lovely, and I really felt like they were easy to understand. And the answer is that possibly Mercury formed looking a bit like the Earth. And then it got blasted either by one huge impact or lots of small impacts, and that blasted away the outer layers of the planet. So you lost the rocky part on the outside. Imagine it had already differentiated. The iron had already sunk to the middle, leaving you with this, with the mantle, the rocky mantle, and then it gets hit. And the rocky mantle disappears, part of the collisions, and you end up with a planet that has more core than you would expect compared to its size. This is great, but MESSENGER really began to investigate this in detail. And one thing it measured was something called the potassium to thorium ratio. And so we've measured this at various bodies in the solar system, and that's what this plot here is: potassium on the y-axis and thorium on the x-axis. And these are selected because potassium is a volatile, so when things start to heat up, potassium will disappear, but thorium won't. And so this can give us some idea about the history of the planets. And I know this plot is a little busy, but what you should take away from it really is that if you look at the orange dots, that's Venus. If you look at the dark gray, that's Mars. The light gray is Mars. And the Earth is there a little bit, at least in green. And those all lie on one line. This potassium to thorium ratio is about 5,500 in those rocks. And then you look at the moon, and that's kind of the blue at the bottom there. And you can see the potassium to thorium ratio is very different, about 360. And so the moon, formed by a huge collision, lost its potassium and ended up with a different potassium to thorium ratio. If Mercury had a similar set of collisions, you would expect its potassium thorium ratio to be lowered. But the data from MESSENGER on that plot are given in red. So you can see that they lie on the same line as the other planets. And this really made people begin to question whether this collision theory could be true. Still, this is a big mystery in the field. People have suggested maybe the inner heliosphere constituents were different. It's hard to manufacture that in the solar system models that are run. Maybe Mercury migrated and it didn't form where we see it today. We do know planetary migration happens in systems, particularly since we started looking at exoplanets. We really realized that planetary migration is fairly common, but really there's sort of no way of resolving this yet, even using migration. So this is still a big mystery. Another one of the questions that MESSENGER was sent to address was the polar deposits. And so this data was taken by the Arecibo radio telescope, and it was looking down, looking at the North Pole of Mercury. And they noticed, this is I think in 1992, they noticed that there were some regions near the pole that were really high on radar reflectivity. So regions that really began to reflect the radio waves back again strongly. And nobody knew what was causing this reflectivity, this high regions of reflectivity. And so when the spacecraft got there, it took really high resolution images of the surface, and scientists overlaid one over the other. And this is what they saw when they did that. And it seems so obvious to us now. What we find is that these bright reflective regions coincide with the craters, very deep. In fact, craters, a special type of crater called a permanently shadowed crater, They occur near the poles of the moon and other planets too. They're very, very deep near the poles, which means the sun can never hit the bottom. And so we saw these on the moon and realized that there was ice at the bottom of these craters. And actually, we suspect that this is the case for Mercury as well. There's solid ice at the bottom of the permanently shaded craters, despite the fact that on the day side, Mercury is at about 450 degrees Celsius. On the night side, about minus 180 degrees. So huge temperature differential across the planet. But still at the bottom of these craters, we think there's solid ice. So this question actually was solved by MESSENGER. There was amazing altimeter data taken. This is MLA data, and you can just see really clearly alongside the images that were taken, we can also see really clearly regions where there's which are heavily cratered, but also regions that are less heavily cratered, suggesting resurfacing of the surface, regeneration of the surface through volcanism. And you'll see as this sort of rotates, there are regions where there are hardly any craters. We'd expect the surface to be equally cratered. So that suggests that the surface is newer in some of these regions. And you can see the differential in elevation there as well. Not super high mountains for me to go after on Mercury. But looking a bit more closely at the surface, again, yeah, we can see regions that have been resurfaced, but we can also see some really interesting features. This is scarps and ridges that we can see, which I'll talk about in a moment. And of course, we can look at, measure and count impact craters. And one of the reasons that we're really interested in looking at the impact craters is that they can tell us something about the surface. So this is the biggest impact crater on Mercury. It's called Caloris. It's that entire orange splodge you can see on the left-hand side of my screen there. And it was formed by a massive impact. And that actually explains a lot, because on the opposite side of Mercury from that collision, there are some very strange, unusual surface features. And actually it's thought that when that collision happened, shock waves went straight through the planet and disrupted the surface on the other side of the planet from the collision. And so when we start to piece all these features together, we can gain a better understanding of how Mercury's evolved over its life. But we can also think a little bit about the age of different features when we compare them to each other. So here we've got impact craters, but we also have ridges, and these wrinkle ridges or escarpments, these ridges form when Mercury cools. And as it cools, I think of it as like its skin gets too big for it. And so the skin starts to wrinkle in different places. And by looking at whether, say, for example, in the left-hand plot there, you can see at the top, let's look at the middle top one there. I need a laser pointer right now and I can't point, but you can see that there you can have an impact crater, and all the way through it you see a ridge. That means that ridge formed after the impact crater. If the impact crater had happened second, it would have obliterated the ridge. And if you can age the impact crater and you know the ridge happened later, and you can do this within enough places across Mercury, you can start to work out the rate of cooling, the rate of contraction, the rate of forming of the ridges. And that tells you something about how fast Mercury cooled and how much it shrunk since it originally formed. The answer is tens of kilometers, we think. And also some really unusual features were discovered which weren't on the original science list. This is one example. We're now looking at an impact crater, and we find these really strange features carved out of the bottom of the impact crater. On the right-hand side, we've just zoomed in on some of these features. They look like they're sticking out at us, but that's actually the strange features are actually holes rather than bits that are sticking out towards us. It's hard to get perspective in these images, but they're really unusual. We haven't seen them anywhere else. They were called the Hollows, which sounds like it's something out of Harry Potter or something. I don't know. I haven't read Harry Potter, but and the other material around it is also unknown. So it was called low reflectance material is what it was named, which means that we don't know what it is. It was outside the range of the instruments that we sent. So there's a lot of mysteries around Mercury's surface, and the composition of this region around the hollows and how the hollows formed and what they are still really open questions. But I'm going to get on to kind of my topic, which is magnetospheres and the magnetosphere of Mercury. I've actually got up here now just a schematic which I stole from the Earth because it just shows us nicely what we're going to be talking about. But Mercury is basically, the system looks really similar to this. So we've got our planet in the middle on our magnetic field, like a dipole magnetic field with field lines coming out of the South Pole and into the North Pole of the planet. Mercury's dipole is in the same direction as the Earth's. And you can see that on this schematic, the sun is to the left. And so we've got the solar wind coming away from the sun all the time, pouring off of the solar surface. And that sort of stretches out this magnetic field into this strange sort of bullet-like shape that you can see here. And Mercury's again looks kind of similar to this. And so this is what I'm interested in, the environment, the larger magnetic environment of the planet. The first thing to note about Mercury, though, this paper was published soon after the MESSENGER arrived, 2011, is that its dipole, the center of the magnetic field, is not at the center of the planet. So if I just kind of, hopefully this is moving now so you can kind of get an idea. The red dots are crossings of the magnetic equator. And you can see that all of these crossings of the magnetic equator occur to the north of the planetary equator. And actually this offset is about 480 kilometers, about a fifth of Mercury's radius. So Mercury's magnetic field is not centered on the center of the planet. It's all shifted to the north. And we have seen this at other planets too, but this is a large offset. We're talking a fifth of Mercury's radius. And actually, this is the reason why, when I said earlier on, you know, the north's going to look a bit like the south. So we'll just look at the southern magnetosphere and then we'll take the mirror image and that will be what the north looks like. This is one reason why that's not really the case, because the offset of the magnetic field relative to the planetary surface causes some interesting features. And so this is kind of a schematic that you can see of Mercury. You can see that Mercury's magnetic field is really weak. So the planet takes up most of the magnetosphere, unlike the Earth, where the Earth is this dot and the magnetic environment is large. Mercury has this really weak field and it's really close to the sun. And so its magnetosphere is much, much smaller compared to the planetary size. And because the magnetic field shifted up to the north, you can see that we have some asymmetries in the field where it encounters the planet. So in the northern hemisphere, those magnetic field lines are really close together near the planet. And in the south, they're much further apart. And that means that it's easier for particles to hit the southern surface than the northern surface. So we're going to get some interesting asymmetries with particles hitting the surface in the two hemispheres because of this offset of the magnetic field. Yeah, as I mentioned, Mercury is sitting close to the sun and seeing this extreme space weather. This is a video actually describing large-scale dynamics of magnetospheres at the Earth, but again, really similar thing applies to Mercury. Thing is, we haven't made these videos for Mercury yet, so I have to use Earth ones. So here we're looking at just a movie showing the solar wind coming off of the sun and ploughing into the magnetosphere, in this case of the Earth, and causing, firstly, ploughing into that side of the planet's magnetic field, but also causing something called reconnection, where field lines change their topology. Basically, energy and momentum from the solar wind enter the Earth's magnetosphere and get stored and build up and build up and build up till they get explosively released. Particles fly down field lines on the night side of the planet, smack into the atmosphere and make it glow, causing the aurora. So the aurora is really caused by the interaction between the solar wind and the magnetic field of the sun and the Earth's magnetic field. Again, just energy and momentum coming from the sun's environment to the Earth, getting stored and then released. And we see the same thing happening at Mercury, but Mercury is a weird beast because, as I mentioned, the core of Mercury is massive. It extends to 85% of the radius of the planet. And so when the solar wind pushes hard against the day side of Mercury, as you would expect it to, actually, we can end up with induction currents, which flow at the core of Mercury and end up kind of punching the solar wind back again. So where we would expect extreme solar events just to push the magnetic field of Mercury underneath the surface of the planet, allowing particles from the solar wind to just smack into the surface, actually, that doesn't seem to happen very often. In fact, when the solar wind pushes really hard, because of this massive iron core, Mercury is able to push back again. And so we see different dynamics at Mercury than we do at the other planets. You have to take into account this huge iron core and these induction currents, which flow, causing some shifts to our expectations. But we do see particles close to the planetary surface. This is a MESSENGER passing through Mercury's magnetosphere, and the top plot here, the bottom is magnetic field and the top is just heavy ions. So we're seeing some plasma, we're seeing particles coming off of Mercury's surface that we encounter, particularly as our spacecraft is close to the planetary surface. As it goes over the northern pole, it's close to the surface, so we see these particles coming off of the surface. So we're interested in the magnetic field and the particles in the environment. Problem is, though, as I mentioned, we get really close to the northern pole and we never see the northern environment. We don't get close to the southern pole, so we can't see any indication of how many particles are hitting the surface in the south very easily. But we do see the broader environment in the south. And so this sort of trade-off in the orbit between all the different competing people who want to see different bits of Mercury's magnetosphere does mean that we have a lot of really interesting open questions left to answer. One piece of work that I was working on recently actually was looking at X-rays from Mercury's surface. I'm interested in X-rays because at Leicester we built an instrument which is currently on its way to Mercury, which is looking at X-rays, and I'll talk about that a bit later. But I was interested in looking at all of the X-ray data taken by messenger. And as I mentioned, I'll just play this movie so you can see on the right-hand side there, we're looking at the Earth and we're looking at the bright aurora, which happens in sort of stripes at high northern and southern latitudes, the aurora borealis and the aurora australis. And that's just because particles, I'm not sure if you can see my cursor actually, but if you can, particles fly down magnetic field lines. They're tied to the field lines, so they can't escape those field lines. They sort of fly down them, and where that field line encounters the atmosphere glows. And so you can see that we get sort of funnels of particles into the northern and southern high latitude regions at the Earth on the night side of the planet that then generate our beautiful aurora. So we weren't expecting to see any aurora at Mercury because it doesn't have an atmosphere, really. It's got a very tenuous sort of exosphere, but there really isn't anything to hit. So we weren't expecting to find aurora at Mercury. But we did plot our location of X-rays. Now we'd expect to see a ton of X-rays on the day side for reasons I'll go into later. We wouldn't really expect to see X-rays on the night side because the X-rays on the day side are caused by the sun. The night side is not illuminated, so we wouldn't really expect to see X-rays. But when we plotted the data out, this is what we found. We're looking at, I've put these two pictures side by side. The right-hand side, we're looking at the Earth from the night side, let's say. The left-hand side, we're looking at Mercury from the night side. So we're looking at night on the planet. And you can see two really strong bands, and these are bands of X-ray emission there. So there's X-rays coming from Mercury's surface on the night side. And if I unwind my planet, so B, the right-hand side, that's looking at the planet, and if I sort of unwrap that, that gives us A, which is a plot where we basically have midnight in the middle, and we're sort of looking towards dawn and towards dusk. We've just unwrapped our sphere slightly. So this is still just the night side of Mercury. And you can see those two bands of precipitation of X-ray emission. What was a real giveaway as to what could be causing this X-ray emission is that if you look really closely there, you can see that I've plotted a dashed line through the middle. And that dashed line is the location of the magnetic equator, not the planetary equator. The planetary equator is at 0. And you can see this dashed line is the magnetic equator. Those two bands of emission are symmetric about the magnetic equator. And so that's telling us there's some interaction between the magnetic field and this X-ray emission. And of course, we later realized that actually this is the aurora on Mercury. Those particles are traveling down field lines. There's no atmosphere to hit, but they're hitting the surface of the planet and causing electron-induced fluorescence, which means X-rays are coming off the surface basically that we're measuring. So the aurora is not visible at Mercury as it is at the Earth, but actually we see the aurora in X-rays at Mercury. And actually, I'm not going to talk at length about this plot, but it's kind of fun because we also sat inside Mercury's magnetosphere and looked for particles that could be causing these aurora. And we found that there are bursts of high energy electrons, which is probably what's hitting the surface and causing the electrons to form. If we sit in the magnetosphere and we measure our location where we see these electrons, and then we use a model to map the location, map ourselves down our field lines to the surface, we get the bottom plot there, B. So B is where we expect our electrons to hit, and the plot at the top, A, is where the X-ray emission was seen. And you can see these two plots are very satisfying. They are in great agreement with each other, suggesting it is these energetic electrons that are causing our X-ray aurora at Mercury. In fact, though, some recent work, which we are hoping to publish in the next month or two, is looking at the fact that actually sometimes at Mercury, we don't just see the particles traveling down field lines hitting the surface. Sometimes entire field lines smash into the night side of Mercury's surface, depositing their particles across a broad region of Mercury's surface and giving us X-ray emission in really weird places like the equator, which is highly unusual. So we have some new data that we're looking at the moment, which is suggesting some really interesting dynamics at Mercury. So looking forward, I've just given you kind of a brief history of Messenger and a few nuggets of magnetospheric physics, but what we're really looking forward to is a mission called BepiColombo. And this is a European Space Agency mission, joint with the Japanese Space Agency, and it's currently on its way to Mercury. The amazing thing about this mission, the thing that is really going to be a game changer actually, is not just the instrumentation is improved. Now we know what we're looking for, but also there's 2 spacecraft that are being sent. So they're sent together in one big package. And when they arrive at Mercury, they split apart. We have a little Japanese magnetospheric spacecraft, which is the small one you can see on the bottom of this slide. It's a spinning spacecraft. It's looking at the environment. And then we've got the one at the top there, the European one, which is a larger spacecraft, which is going to orbit close to the planet. So now we have a spacecraft designed for each of those 2 kind of competing areas. We've got one looking at the environment and one focusing on the surface. And it's designed to do kind of similar things to Messenger in some senses, although a lot better. And now we understand what we're looking for. Again, we can do more. But again, study things like surface processes, the dynamics of the magnetosphere, characteristics of the magnetic field, the atmosphere, the exosphere, the composition and the structure, etc. This is the launch. I actually got to go and see it launch in French Guiana. I've only ever seen one mission launch before, so I was pretty excited. It was a night launch from the European Space Agency spaceport in Kourou. And I wasn't this close, by the way. I didn't take this photo, sadly. I was many kilometers away, but incredible to see this thing launched. As I mentioned, we built one of the instruments on board the European spacecraft. There were 11 in total, and we built one at Leicester, and so that's how we got to go and see the launch. Also, it sort of adds to the nerves as you're sitting there watching your spacecraft about to launch, given the fact that the group had spent 20 years building an instrument that's sitting on there. And I'm hoping I'm going to spend the next few years of my career working on the data. So how does it get there? It's hard to get to Mercury. This is the cross you can see is the spacecraft. So this is going to take a while to go around and around. You can see we do many, many laps, I think 19 laps of the solar system in the course of getting to Mercury and getting in orbit around it. I could launch the spacecraft straight towards Mercury and would get there fairly quickly, the order of months probably, but the issue is stopping basically. So as you head towards the sun's incredible gravitational field is going to make it really hard to stop at Mercury, which is a really small planet with very low gravitational field. And so instead of going straight for Mercury, we go round and around the solar system, and every time we go around, you can see we use gravitational assist from the planets to change our trajectory and our velocity. We fly past the Earth. We flew past, actually, I think the 10th of April, 2020. Then we flew past Venus in October. We'll fly past again next August. And then we start flying past Mercury. And we'll do 5 or 6 flybys of Mercury before we finally get into orbit around the planet. So this, again, it takes 7 years. So it launched in October 2018, and it will arrive in December 2020. I promised that I would sort of talk a little bit about observations made en route. The big announcement of phosphine observed at Venus came a month before our flyby. So obviously, as soon as this announcement was made, people had looked using ground-based telescopes. They've been looking at different wavelengths of radiation from the Venetian atmosphere, and they'd observed that there was a bite out at the right wavelength for phosphine. Using a couple of different sets of instruments. So then there was much excitement because phosphine can be a biomarker, although it can be caused by lots of other things as well. So immediately we thought, well, we're flying past in a month, so I wonder if we can have a look and see if there's anything there. The answer is that the first flyby of Venus really had a negligible opportunity to observe any possible fingerprints of phosphine, just due to the geometry. But the second flyby, which will be August 2021, will have a much more favorable geometry. So we'll certainly be looking out as we fly past in August. When it gets there, what will happen? Well, our transfer module, which is sort of the life support system for the spacecraft, detaches, and that's done its job now. The 2 spacecraft separate, so we've got a sun shield. We eject the Japanese spacecraft from the sun shield. It had to be protected en route because it's designed to spin, and it's not spinning in the journey. So it's protected by the sun shield for the journey. It gets released, heads around, and deploys its antennas and its booms. Then we get rid of the sun shield, and then the European spacecraft is ready to go. And so that's what will happen in 2025. This is what it looks like in terms of the orbits. And I wanted to show you this because this is really going to show you kind of the advance of two spacecraft. So not only are we able to see the north and the south equally well, the surface by the European spacecraft and the broader environment from the Japanese spacecraft. So we don't have that trade-off anymore. We'll see a much more symmetric picture of the system, which is important because the system is intrinsically asymmetric. But also we'll be able to do things like cause and effect. There'll be times when the Japanese spacecraft is sitting in the solar wind just upstream of the planet, and it sees something big coming our way, and then we're able to see the results on the planet using the European spacecraft. Previously, we haven't been able to do that because the timescales of the dynamics at Mercury are so short that we either see what's coming or what happened, but we are unable to see both at once. So you need two spacecraft for this at Mercury, just because the timescales are so short for the dynamics. And so we'll be able to do this for the first time. So I'm excited because of the symmetry, and I'm excited because of the two spacecraft measurements. This is a picture of the instrument that we built. On the top right-hand side here, the bottom is my Lego model. Just trying to show you that we're the blue brick on the bottom of the European spacecraft there. On the left-hand side, you can see at the Science Museum have the structural thermal model. So you can see a sense of scale. It's 7.5 meters high. There's the sun shield you can see on the top, then the European module, and then the transfer module at the bottom there. The Science Museum will have it, I think, on long-term loan, so you can go and check it out. Just to give you a sense of scale. And our instrument is designed to look at X-rays coming from the surface, predominantly from the day side. So we have X-rays coming from the sun that hit the surface of the planet and cause the surface of the planet to give off fluorescent X-rays that we then collect and measure. And the thing about these X-rays is that the energy of the X-ray that we detect is like a fingerprint for the particle that gave off that X-ray, the atom that gave off that X-ray. So we collect all the X-rays we can from the surface. They're being emitted all the time. We look at the energies, and that tells us what the surface is made of. So for the first time, we have a broader energy range than we've ever had before. We should be able to detect more elements on the surface of Mercury and get a really great picture of what it's made of. I've already kind of mentioned this when it launches and when it arrives. Oh yeah, so on the front of this, these look like kind of glass plates. The reason that we've been able to miniaturize the technology required to make these measurements, to make this X-ray telescope, is that those glass plates actually have tiny holes in them. They're called slumped microchannel plates. They have tiny channels, and 20 micron channels in them. And those guide the X-rays to the detector. So X-rays are really hard to focus. And these tiny channels focus our X-rays onto our detector, which allows us to miniaturize the technology compared to previous instruments that have been launched. The way it works is that if you have an electron ejected from an atom, another electron will fall down into that lower energy level and give off an X-ray, which is what we measure. And that's why every X-ray we can link back to an element that gave off that X-ray, because the energy levels, the electron energy levels inside the atoms are different for each atom. So the amount of energy your X-ray gets is different. I'm really interested in looking at craters. We have a project looking specifically at craters because they tell us something else about Mercury. So here, all I'm going to do is, this is just like a demo I do with kids, but I've got layers of colored powder here and I'm dropping an impactor in. And you can see that there's some yellow powder under the blue powder, and you get this kind of pattern. These are called rays, this characteristic pattern of ejected material. And if you look at the left-hand side here, this is a picture of Mercury's surface. You can kind of see some craters and some rays there. We want to know what these rays are made of, because this stuff came from under the surface of Mercury. And so if we can work out what this ejected material is made of, we'll get some idea about what the subsurface composition of Mercury is. And that's not an easy measurement to make. And our instrument will have such great resolution and amazing energy range that we should be able to look at things like this for the first time. Okay, so that's kind of a summary of the BepiColombo mission and where we are now. We're currently, I don't know where we are now actually, but we're heading past, we headed past Venus a month ago. We're going to go past again in August. Our instrument is not switched on because it can't take any measurements until it gets to the planet. So actually, we take some data from it once every few months to check its health. And we have a calibration source on board that we can use to check how things are going, but we won't be able to take any science data until we finally get to Mercury in 2025. All right, so I'm going to end my talk there. It's a bit of a whistle-stop tour of Mercury's environment, but I'm happy to answer any questions if anyone has any, so please feel free to ask away. Thank you.
Well, thank you very much, Susie. That was an excellent talk, and I think I'm a little bit breathless now. It's about to get a little bit more complicated because I can see the first few questions are with um, partly to do with mountain climbing,
Oh,
partly
great.
to
Love
do
it.
with Mercury, and some.
Yeah. We can talk about mountains.
So, so yeah. So let's see how we go. First one then is from Jonathan Daniel. Can we land a lander on the poles of Mercury without it melting?
Oh, yeah, good question. So we're currently talking about possible lander. Oh, I think, let me just, something just strange happened to my screen. Yeah, we're talking about future missions, actually future landing missions, and thinking about where we might want them to land and what we might want them to look at and where it's realistic for us to be and what the temperatures will be, etc. It's going to be a massive challenge, but people are already thinking about possible landing sites and how it could be done. Of course, you run the risk of either freezing or roasting, because if you land in a permanently shadowed crater, then you're in an extremely cold environment. If you land on the surface, then you go from hot to cold. So there's sort of no winning really, but people are already starting to think about it. Yeah.
Okay. Now, the next two I'm going to combine together. I think they're about mountains on Earth rather than you might have found on Mercury.
Go for it.
But with your supercluster computer and code, did you get to name any of the mountains in South America?
That's a good question. Yes, you can. If you find them, you can name them, especially if you're the first one to climb them. That kind of gives you dibs on that. But we sort of learned from history, because previously what people have done is go and climb mountains in other countries and then name them after themselves, which doesn't go down well. So actually there are no mountains named after me. We name them all after kind of local features. So if there was a lake maybe that had a name somewhere in the vicinity, for example, or a local feature that already had a name, we would take that name and name the mountain after that, rather than naming them all after themselves.
And I suppose the next one's quite related to that, is what is your most challenging personal mountain climb?
A mountain, actually the one that was on my first slide, a mountain called Cerro Alto. 2017 peak. Well, actually, this is a difficult one to answer, but a 2017 peak, which was actually a second ascent, but had never been climbed from Argentina. It had only ever been climbed from Chile. And we decided to try and climb two 6,000ers in one push. And there was a big ravine between them, and the ravine looked like it was made of rock from Google Earth. You sort of zoom in as much as you can. And anyway, it was made of ice. It was a glacier with a thin coating of rock on the top. And so it's crevasse riddled and nasty. And there's only two of us, which isn't ideal for moving over crevasse fields. And we ran out of food, and a massive storm hit, and we hit some severe penitentes, and we hit blue ice, and just disaster struck in every possible way.
If it could go wrong, it would.
Yeah. There was almost nothing else that could go wrong that allowed us to get back in one piece, which we did. But it was, a sort of traumatic few weeks, I have to say. So that's probably the worst.
And you did manage to climb the second one?
We did manage to climb the second one. After all the disasters struck, we did cross. Yeah, we crossed, and we crossed and we found this beautiful freshwater lake when we just run out of water. Just things kind of happened in the end to allow us to get there.
Well, it's okay to come home, if it looks too dangerous. Anyway, so right, what have we got? Back to Mercury now, but there's still a mountain theme. Are there mountains on Mercury?
Yeah, there are some interesting
high spots, but are there sort of mountain type thingy?
Yeah, well, yeah, sort of. Not, I mean, the mountains on planets, the way that mountains grow on planets depends on their sort of drivers. So some of the major drivers at the Earth, plate tectonics, don't happen on the other planets. So they can't be formed in the same way. But also they depend, this is kind of interesting, but they depend on their planet themselves. So like Mars doesn't have much very strong gravitational field. It's got a really thick crust and something called hotspot volcanism. So volcanoes form in the same place and just keep spewing out material. Because the crust is so thick and because the gravitational field is weaker, it can grow larger mountains and support their weight because the crust is able to support them and because the gravitational field is lower. And on the Earth, a mountain as big as Olympus Mons, which is 3 times the height of Everest, would just sink down into the planet. So there's sort of lots of reasons why mountains are different on different planets. Mercury's are pretty unimpressive, I have to say. So
okay, wait for another crater to form then.
Yeah.
And here's one from Bill, which is about Venus, and this time it's about atmospheres. And the question is that with what we're told about atmospheres requiring a magnetosphere to protect them, how is it that Venus's atmosphere is so thick without it having a
Brilliant
magnetosphere?
question. That's a brilliant question. Yes, so we all heard about how magnetic fields protect atmospheres and stop the solar wind from stripping away the atmosphere of the planet. And we heard about probably how Mars formed in a similar way to the Earth, and then its magnetic field switched off 4 billion years ago, and then its atmosphere disappeared and everything went wrong. And then we look at Venus, no intrinsic internal magnetic field, no dynamo, but an amazing atmosphere. The answer is that there are two types of magnetosphere that can form. One is due to the dynamo inside the planet, and the other is called an induced magnetosphere. And it basically means that as a solar wind comes in, it flows around, it gets the outer regions of the atmosphere are charged, and so they form this induced magnetosphere in essence, which is like a magnetic cavity around the planet. They're much smaller than the magnetospheres you form when you have an internal magnetic field like Venus, like Mercury, and like the Earth, and like Mars had. But they are observed, so it's due to Venus's atmosphere.
Okay, and that leads, he's actually asked a two-part question. That leads nicely into his second question, which is, as for Mercury, is its magnetic field a fossil field or an active one?
An active one. Okay. Although it's a good question because as it's a small planet, you might expect it not to have much of a magnetic field left anymore and to be almost all solid, the core to be almost all solid. Actually, that's not the case, and probably due to impurities in the core. So iron plus other things, other impurities change the freezing point of iron, and so that's probably how it's not.
Okay. Okay, and now a simple geometry one. If I stand on the Earth, well, here we go. There's a question of how big the sun is in the sky at Mercury.
I have no idea. Excellent, no clue. Massive.
Well, okay, so I think it might be just in proportion to how close Mercury is.
Yeah, and that varies between half of the distance from the sun to the Earth and a third of that distance.
Yes. Now, I can see time's moving on, and at the bottom of the chat screen there's 70 new messages. So I'll skip another one from John. But do we have David Southwood in the audience today? I suppose he'd have to type in yes if he's there. Right, but what I'll do actually is I'll drop down to the bottom of the screen. One interesting question perhaps for you is from Alris, and slightly out of topic, but is coding an important skill for experimental and theoretical physics? And which language would you recommend?
Which language would you use? Yeah, so I learnt to code in a programming language called IDL, which, there's Dave Southwood, he probably knows exactly what I'm talking about. But these days, most people code in Python. So Python's a good language to learn if you're interested, and it's a really important skill for experimental, theoretical, data analysis, all of those things.
Okay, over to David, if you have a question ready, if you want to unmute yourself, or I can fill in some time if you're thinking. You're on mute, by the way. All right. So
needed you to unmute me, John.
Oh, is that right? Oh, God. I didn't actually do that in the end because I forgot I was co-host and Bill did it.
I don't want this to get out in the community. You know, my wife has been looking for ways to mute me and unmute me for years. But anyhow, I am now
unmuted. Only happened virtually, David.
Yeah. And what a magnificent talk, Suzie. Absolutely riveting. I very much enjoyed it, and I'm looking forward now to BepiColombo actually arriving. I mean, it's
5 years
on my list of things to look forward to now. You really sold it to me.
Ah, thank you. I'm about trying to get some more Mercury fans. There aren't many out there. I've got 5 years.
No, it's true. And possibly don't know, but I tried to cancel BepiColombo because it was too expensive.
Calm down now.
So probably, that's the end of my career, but I think my career ended some time ago. But no, it did rather overrun its budget.
And it's time.
And, but
it was a little late,
actually, the ESA member states overruled me. And so
glad to hear it.
there you are. I tried to get out of Europe, and they wouldn't let me. But it was touch and go for BepiColombo.
Oh, interesting.
Now I realize it's a really wonderful thing to be doing. Now it's off and rolling.
Yeah,
absolutely marvelous. Very exciting. I don't know, John. Do we want to wrap up at this point? Because before we wrap up,
There's just a couple more actually, and one that relates to both of you. So unfortunately now, David, I know you said that you're in the firing line yourself, and the question is to Suzie, but then you'll probably answer it. Do you plan research on other planets beforehand, or do scientists take advantage that there's something already going on to request information to be taken from other planets' comets? So how does it work?
So we have an instrument that's designed to answer a science question, and we have a set of something called a science traceability matrix, which goes from kind of what we need. This is what we're trying to answer. This is the data that we need to take, and this is how we're going to take that data. So we have very specific plan in place to take the data we need to answer the science questions. On the other hand, when they started designing the instrument that we built to go to Mercury, we didn't know that there was any X-ray aurora. We only discovered it in 2016. They started building the instruments over a decade before that. And so now we know there's X-ray aurora at Mercury. There's a whole new field of physics, magnetospheric physics, that we can tackle, not just surface composition, but now magnetospheric physics and dynamics. And so now we're rewriting where we'll be looking and where we'll be collecting data to take into account the fact that the field has evolved since the instrument was designed. So a bit of both is my answer. David might have more insights on this.
Yeah, no. I mean, how do we choose where to go is the first question. And that requires basically competition across the science community. So scientists have to kind of argue amongst themselves to rise up the priority list. And so, they're really, it's not a random choice. It is pressure from the science community that this is where we need to go to understand our solar system better. But as Suzie just said, you generally find when you've got somewhere, or even before you get there, that actually what you've said you're going to do isn't quite what is going to happen. I mean, one of the most delightful things about exploring the planets is basically all the theoreticians who told us what the planets were going to be like got it completely wrong. And so people like Suzie and all the other people who build instruments for spacecraft have had the great pleasure not only of finding new things, but also showing how weak our understanding of the planets was. If you ever had any doubt that this is a worthwhile thing to do, for me, the very fact that we, when I was 9 years old, my mother gave me a book about the planets. Everything in that book was wrong. That is one of the great things about living at this particular time. And it's taught us an enormous amount. Planets are incredibly complicated, and it is not possible to solve the problem by just thinking about it. You have to go there, you have to sniff the atmosphere, you have to scratch the surface, all the things Suzie was telling us about in the case of Mercury. And, frankly, that tells us then a great deal about our own planet. Once upon a time, all the planets came from the same place, sort of out of the sun. They're all linked. we need to understand how they all fit together. Do you agree,
Okay.
Suzie?
Yeah, and I think actually just to add one thing, it also helps us understand the exoplanets that we're starting to observe elsewhere in the universe. If we can't understand our own solar system, how can we possibly try to characterize planets orbiting stars so far away? So,
Well, that's absolutely the thing that
That's right.
knocked me sideways towards the end of my career. For a long time, when I was a student, when I was even your age, Suzie, you weren't allowed to talk about life anywhere else.
right.
Now we talk about little else, to be perfectly frank, and I find that much more fun.
Can I just finish with 2 points? One from Harrison, one from Linus. I think Linus is more ambitious. He'd like to get an internship at NASA. And do you have any advice for someone like that? But then also from Harris, who's an A-level student, and his question, if I can scroll to the right bit, as well as studying, what other ways are there to find opportunities to broaden experience in space exploration? You've, Suzie, David, you've both been people who've grabbed the world and whatever's beyond the world and run with it. So how do you do that? How do you go from being a normal earthling to a dreamer?
Well, listen, I don't think Suzie's a normal person, actually. But I am, and I've got a very simple, two simple principles. One is never say no to a possibility.
That's what I was going to say.
If that looks interesting. So, you know, you've got to be prepared to move in whatever direction looks to be opening before you. And the other thing is, I've always felt I had a 20% chance of getting any position, any job, studentship, whatever. So always make sure you're applying for 5 at any one time. And frankly, that shifts the risk very dramatically. So 2 rules: never say no to something that interests you. Second rule, always have 5 options in front of you. You know, if you actually focus on one, the odds are likely you're going to be disappointed. If you focus on 5, one of them will turn up, but just make sure you're going to enjoy whichever one turns up. Sorry, I talked over you, Suzie, and you are a normal person, I know, but...
No, your advice was exactly what I was going to say. I was going to say, take on the opportunity that comes your way, because, you know, you might regret it later if you don't just take a chance.
Can I add to that as well, Suzie? The one you mentioned, transferable skills from all the other things that you've done, and the one transferable skill that's helped me with my own life and is relevant to this particular one is always ask the question of somebody you don't know. It's more likely than you think that they'll get back in touch with you and answer your question. The world is a more open and a better place for people to talk to each other than you might suppose. So Harrison, Linus, start typing those emails.
Yeah, good luck.
Thank you very much.
Get to it.
So over to Rod or David now for some closing words. Or Bill.
I'm the one you've unmuted, so shall I pick up the torch?
Yes.
Suzie, that was a wonderful talk. I really was riveted the whole time, and I've heard you talk before, but I still enjoy it. And I love the way you built your own career, your own experiences into the joy of science. That was absolutely wonderful. I'm sure everybody who's been listening would want me to say how much we've enjoyed it. And the second thing I'd say is, do come back sometime. You know, please remain a friend of Imperial College. It's not such a bad place. And we've been very happy to have you here. Then finally, as I'm the point of taking over from Rod, as the chairman of this organization, let me in front of everybody say what a wonderful job Rod has done over 18 years, I believe, building this Friends of Imperial activity from nothing. For me, I've been absolutely delighted every time I've been involved. And for me, Rod, you've done a brilliant job. I think you're going to remain some kind of emeritus chairman or something, emeritus president, I don't know. Whatever it is, we'll be looking to you to make sure we stay on the straight and narrow. And thank you from everybody involved for your efforts over that time. Thank you.